S. And your P elements, so the S is the first two columns, the P are the last six. The transition metals are the middle of the periodic table, that's your D elements there. The lanthanides and actinides are the F, which are the very bottom two rows of the periodic table. Last thing to mention are the noble gases. The noble gases are the far right-hand column, helium on down. Again, those are the ones we typically say are stable at the condition that they're in. Next thing that this chapter talks is about electrons. So you have two common ones, valence electrons, which are your outer, or inner electrons, which are your core electrons. The valence electrons are the ones that really determine how things react and how things bond. Core can deal with light though. The other thing that mentions within electrons is some things need to be bonded to themselves. So it talks about the diatomic elements. If you remember from Chem 1, we called it Hunkelbrief. So hydrogen, oxygen, nitrogen, chlorine, bromine, iodine, fluorine. Those are the 7 elements that are so reactive, they have to be bonded to something, and there's nothing else available to bond it to themselves. 2 of them that we don't talk about in Chem 1 and Chem 2, though, are phosphorus and sulfur. These are not diatomics. Phosphorus you'll commonly see as a P4. So P4 is what phosphorus is on its own. Typically, again, a lot of elements in metals can just be on their own, not phosphorus. Sulfur you'd see as an S8 would be the common way to see sulfur. Again, very unusual at some of these nonmetals how they work, but again, it's just dealing with how they're more stable. And a lot of metals are stable on their own. Nonmetals are oftentimes need to be bonded to something. The next thing that this talks about is electron configuration of ions. It refers to the fact that representative elements, ions are typically isoelectronic with noble gases. So for example, if you look at the periodic table, you have fluorine, element number 9. If it's F-1, it gained an electron, it's isoelectronic with neon. So that term isoelectronic just refers to the same number of electrons. So it's trying to be like a representative element. Transition metals, on the other hand, are a little unusual. Rarely are isoelectronic with noble gases, sorry for the typo there. Transition metals will lose S electrons first, which is kind of unusual. So when we talk about looking at the charges of a metal, you'll notice like on iron, iron can be a +3, a +2, or a +6. The electrons it loses first are usually the S electrons. Most transition metals are a +2 possibility for a charge, because if they lose those 2 outer S electrons, they're at a noble gas configuration. One of the things we don't get into, I believe, at all for AP Chem, is later on in chemistry, is that some things can be stable with half-filled orbitals, and that's where the 3 and the 6 charges come in for the iron, if it lost electrons. The next thing it talks about mainly is the trends of the periodic table and how they vary. They refer to something to start off with, though, as effective nuclear charge, which is the charge felt by an electron from the nucleus. Remember that a nucleus has positive protons in it, so it's attracting the negative electrons. That's the nuclear charge, what it's attracting to. Recall electron shielding is something that we mentioned. More shells of electrons between your nucleus and your outer electrons, the less the charge, the effective nuclear charge can be, because there's shells of electrons preventing it from holding on. The first trend that it talks about is atomic radius. So in general, for atomic radius, what we often do is have students draw an arrow going left to right and saying as you go left to right in the periodic table, atomic radius decreases. The reason why atomic radius decreases as you go left to right is because you're gaining more positive protons in your center, but you're not getting any more shells of electrons. So there's a larger effective nuclear charge. Now on the other hand, as you go top to bottom on the periodic table, atomic radius increases. Radius increases as you go top to bottom because you gain more shells of electrons as you go down further. The ionic radius is something that's mentioned as well. It deals with cations and anions. The trend of that's a little tricky because it depends on if you're gaining or losing electrons. So that one I'm not going to get into too much, other than if you understand atomic radius and that idea that protons and electrons determine how big you are across, and then shells of electrons determines the second part, you can probably figure out that one on your own. Usually you're going to have things that are positive ions losing a shell of electrons, so then they're going to be smaller. Negative ions usually actually going to be larger than their counterpart. Ionization energy is the next thing that's mentioned. Ionization energy is defined as the minimum energy required to remove an electron from the gaseous phase into its ground state. So how much energy is required to lose an electron? Now there are things called first, second, third ionization energy or ionization potentials. First ionization potential would be energy required to lose 1 electron. Second ionization energy would be energy required to lose a second electron. Third, so on and so forth would be that. Now the trend for ionization energy, so again if we're doing our top down or left to right arrows, as you go down the periodic table, ionization energy decreases. The reason why it decreases as you go top to bottom is because the atoms are getting larger. And if they're getting larger, it's easier to lose an electron because it's further away from its nucleus. On the other hand, as you go left to right across the periodic table, ionization energy increases. As you go left to right, ionization energy increases because the atoms are getting smaller. And if they're getting smaller, the outer electrons are closer to the nucleus so they can pull in on those electrons more. The last trend mentioned in this chapter is electron affinity. Again, electronegativity will be covered later. Electron affinity is the negative of the energy change that occurs when an electron is accepted by an atom in the gaseous phase. And what you can write down for the trend part is it's the exact same as ionization energy. As you go down the periodic table, electron affinity decreases. As you go left to right, it increases. So in other words, things that are in the upper right-hand corner are very good at taking in electrons. And remember, with electron affinity, the other thing I jot down for a note is large positive values. So big plus values are good. Because again, the original energy value is usually negative, but if you take the negative of that energy, big positive values are good. Last thing to mention that I'm not going to go over completely is this chapter goes over each group of the periodic table. So remember, a group is a column down the periodic table. So it talks about some things that each of the groups have in common. Now again, like your alkali metals, they're all metals, all very reactive. Alkaline, a little less reactive, things of that nature. That would be something that's just going to take a little too long to go over here. But you can always look back and remind yourself of. The thing to keep in mind though is not every column in the periodic table behaves exactly the same. Especially when you get to the P side of things, because you're going to have some metals and some nonmetals in the same column. Take carbon, for example. Carbon's in the same column as lead. That since they're in the same column, it doesn't necessarily mean they behave exactly the same, but they are similar. And that is chapter number 8 on chemistry review of the trends of the periodic table. Maddie, this is where you now hit the